In the last lecture, if you are remembering, we have done the Fourier series for half range. That is, whenever a function is defined in 0 to L, then the function f x, which is defined in 0 to L, can be expressed as a Fourier sine series or can be expressed as a Fourier cosine series. Whether we are expressing it as a in terms of cos functions or in terms of sine functions, in 0 to L the graph of the function will remain same, whereas in 0 to minus L it will be changing depending upon whether you are using the sine series or cosine series. Now, in this particular lecture, we will study a theorem which we call as Parseval's theorem, and after that we will show it that what are the applications of Parseval's theorem. So, Parseval's theorem states that if you have let f x be a periodic function with period 2 pi and defined in the interval minus pi to pi, then there is a little mistake. In that case, there will be 1 by twice pi will come. Let f x be a periodic function with period 2 pi defined in the interval minus pi to pi, then 1 by twice pi minus pi to pi f x whole square dx. This is equals to a 0 square by 4, this will be a 0 square by 4 plus half into summation n equals 1 to infinity a n square plus b n square, where a n and b n are Fourier coefficients of f x, provided the Fourier series of f x converges uniformly in minus pi to pi in the interval minus pi to pi. So, therefore, what is happening? If f x is a periodic function with period 2 pi, which is defined in the interval minus pi to pi, then 1 by twice pi minus pi to pi f x whole square dx, this is equals a 0 square by 4 plus half into summation n equals 1 to infinity a n square plus b n square, where a n and b n are coefficient of f x, provided the Fourier series for f x converges uniformly. Please note this term, converges uniformly in minus pi to pi. So, that if you see the next one, if I go to the next slide, what is uniform convergence? Just I am giving the definition of uniform convergence. The series summation n equals 1 to infinity u n x is said to be uniformly convergent in the interval a b if for a given epsilon, very small number greater than 0, a number capital N which can be determined, which is independent of small n, such that for any x you take in the interval a to b, the absolute value of s x minus s n x is less than epsilon for all n greater than capital N, where s x is the sum of the series and s n x is the sum of the first n terms of the series. So, please note this one, that s x is the sum of a series and s n x is the sum of first n terms of the series, then if modulus of s x minus s n x is less than a very small quantity epsilon, which is greater than 0 for all n greater than capital N, then we say that the series this one summation n equals 1 to infinity u n x is uniformly convergent. So, you may ask us why this uniformly convergent concept is required for us. The reason for uniform convergence is nothing but, you will see whenever I am taking the series, Fourier series, and if we try to make the term by term integration will be possible whenever we want to, if the series of f x is uniformly convergent, and for that reason this particular assumption has been taken care of in this particular case. Now, let us see here, for the proof your f x is defined as like this. F x you can write down a 0 by 2 plus summation n equals 1 to infinity a n cos n x plus b n sin n x, a n cos n x plus b n into sin n x. So, once I am writing this, your series you can write down in this form. Now, you multiply f x by this particular equation, you multiply by f x on the both side and integrate from minus pi to pi, and whenever I am integrating from minus pi to pi each term, then the concept of uniform convergence is coming. So, what you are doing? We are now multiplying by f x on both side of the equation, on both side of this equation. So, if n, then integrate from minus pi to pi, so that you will obtain minus pi to pi f x square dx. This is equals to a 0 by 2 will come outside, a 0 by 2 into minus pi to pi f x dx. We have multiplied by f x on both side plus summation n equals 1 to infinity, summation n equals 1 to infinity a n into minus pi to pi f x cos n x dx plus b n into minus pi to pi f x into sin n x dx. So, what we are doing here? We are simply, I have written the Fourier series of the function f x in the form of a 0 by 2 plus summation n equals 1 to infinity a n cos n x plus b n sin n x. Now, multiplying this equation by f x on both side and term by term integrating from minus pi to pi. Now, this term by term integration of this series on the right hand side is possible only when f x is uniformly convergent, and for that reason the assumption has been taken that f x is uniformly convergent in the given interval. So, once I am doing it, I will obtain this equation minus pi to pi f x whole square dx equals this quantity. Next, therefore, minus pi to pi f x dx equals what I will obtain? Minus pi to pi a 0 by 2 dx. Your original equation was f x equals a 0 by 2 plus summation n equals 1 to infinity a n cos n x plus b n sin n x. That integration, original equation of the series, that I am multiplying, now I am integrating minus pi to pi, and then only I will get this one. So, that plus summation n equals 1 to infinity a n into minus pi to pi cos n x dx plus b n into minus pi to pi sin n x dx. So, sin n x into dx term will come into dx. So, please note that my original equation, whenever I am getting it, my original equation was f x equals a 0 by 2 plus summation n equals 1 to infinity a n cos n x plus b n sin n x. Now, I am multiplying both side of the given equation, I am integrating both side of the given equation from minus pi to pi, and I will get this one. Now, if I evaluate the integral, I will obtain a 0 by 2 into x minus pi to pi plus summation n equals 1 to infinity a n into sin n x by n, sin n x by n minus pi to pi I will obtain, plus minus term will come, since sin n x I am multiplying integrating, minus b n into cos n x by n minus pi to pi. I am obtaining this thing, and I know one thing, sin n pi is equals to 0 for all n, and also cos n pi, which I can write as cos of minus n pi. If I use these two terms, then you will see this term and this term both will vanish. If I use this, sin n pi equals 0 and cos n pi equals cos of minus n pi, then these two terms will vanish, so that you will obtain a 0 by 2 into 2 pi, and which is nothing but pi into a 0. So, once from here I can tell what is the value of a naught. Basically, what I want to do, I have to find out the values of a naught, a n and b n, like we did for the original Fourier series evaluation. We did the same thing. Here also we are doing the same thing. We are just multiplying first by f x, by integrating both sides of the given equation from minus pi to pi. I am obtaining minus pi to pi f x dx equals pi into a naught. So, that a naught you can write down 1 by pi minus pi to pi f x dx. My next step is to find out the value of the coefficient a n. For that one, you can write down your f x equals a naught by 2 into cos n x. I am multiplying, this again the original equation, I am multiplying by cos n x on both sides of the given equation. So, that you will obtain a 0 by 2 into cos n x plus summation n equals, say k equals 1 to infinity. Since I am multiplying by cos n x, so I am changing this value. So, a k into cos k x, a k into cos k x into cos sin x, cos n x, plus b k into sin k x into cos n x. This I can write down. So, multiplying both sides of the given equation, I can obtain this thing. Now, this cos term, this sin term, I can break it and I can obtain it. 2 terms of cos over here and 2 terms of sin over here. Now, on this integration, now on this equation, if I wish, I can integrate it from minus pi to pi. So, that I can write it as f x into cos n x dx plus a 0 by 2 minus pi to pi, a 0 by 2 into cos n x into dx plus minus pi to pi this into dx. So, effectively what I am doing, I am just first multiplying by cos n x on both sides of the given equation and then integrating term by term from minus pi to pi, and I can evaluate the integral which we have shown earlier, and in this way I can obtain the value as pi into a n. The value of this one is pi into a n if I evaluate the integral. This we have done earlier, so I am not repeating that process. So, that from here you can write down a n equals 1 by pi minus pi to pi f x into cos n x dx. And on the same fashion, I can show that if I multiply the given equation by sin n x and then integrate both sides of the given equation from minus pi to pi, in that case I can obtain minus pi to pi f x into sin n x dx. This is equals pi into b to the power n. So, I can obtain this thing, that pi into b to the power n b n. So, that b n will be equals to 1 by pi minus pi to pi f x sin n x dx. So, the values which I obtained of a naught, a n and b n, now I can put it in the original equation, and after putting in the original equation, I will obtain this thing. My left hand side is minus pi to pi f x whole square into dx. This is equals to a 0 by 2 into pi a naught plus summation n equals 1 to infinity a n into pi a n plus b n into pi b n. So, by substituting the values of the integrals whatever I got earlier, by substituting those integrals I am getting these equations, and this is nothing but 2 pi into a 0 square by 4 plus half into summation n equals 1 to infinity a n square plus b n square. And this we can write it as 1 by 2 pi, I can bring on this side, and I can write down 1 by pi into f x square dx. This is equals to a 0 square by 4 plus half into summation n equals 1 to infinity a n square plus b n square, which completes the proof of Parseval's theorem. Therefore, the Parseval's theorem states that 1 by twice pi minus pi to pi f x whole square dx, this is equals a 0 square by 4 plus half into summation n equals 1 to infinity a n square plus b n square. So, let us see now, just I will give you the quickly I will give you the summarization. Fourier series we are writing in this form, f x equals this. Now, I am multiplying both sides of the given equation by f x, and I am integrating term by term minus pi to pi. So, that I will obtain this equation, and on this equation what I will do now, I will try to find out the value of minus pi to pi f x dx, then minus pi to pi f x cos n x dx, and minus pi to pi f x sin n x dx. These three values I will try to find out, and I will put it in the given equation what we have shown earlier. So, that minus pi to pi f x dx, this value I can obtain from where? From this equation. Here if I multiply, integrate from minus pi to pi the original equation, f x equals a 0 by 2 plus summation n equals 1 to infinity a n cos n x plus b n sin n x. So, by multiplying this I am obtaining this, and the value will be equals to a 0 by 2 into 2 pi. Therefore, this is nothing but pi into a 0. So, in the earlier equation minus pi to pi f x dx, this value you can substitute by pi into a naught. In the similar fashion, next I have to find out minus pi to pi f x cos n x dx value. So, the original equation I will multiply by cos n x on the both side, and I will integrate from minus pi to pi. So, your f x is this one, and from here if I integrate, I am not showing this thing, the value you will obtain as pi into a n, and in the same fashion minus pi to pi f x sin n x dx, the value will be pi into b n. So, that this equals minus pi to pi f x whole square dx equals, I will obtain this, which we can write down in this particular form. This will be a 0 square, this will become a 0 square by 4, this will be a 0 square by 4, and plus summation half into summation n equals 1 to infinity a n square plus b n square. And if I just next is this one. So, that 1 by this will be again, that is a change, this will be 1 by twice pi, and this will be a 0 square by 4. 1 by twice pi minus pi to pi f x whole square dx, this equals a 0 square by 4 plus half into summation n equals 1 to infinity a n square plus b n square, which completes the proof of the Parseval's theorem. Let us see now the applications of this. There is one thing which we call as root mean square. The root mean square or RMS of a function f x over an interval a b we define as the RMS of f x is root over a to b f x whole square dx by b minus a. So, please note that RMS or root mean square value of a function f x equals root over a to b f x whole square dx by divided by b minus a, and this value actually a to b f x whole square dx, this value we can obtain using the Parseval's theorem. This RMS value is sometimes also known as the efficient value of the function, and the Parseval's theorem gives then the value of RMS of f x in terms of the Fourier coefficients, and it has many applications. One, two applications are theory of mechanical vibration or electric circuit theory. This RMS concept is used widely, and this RMS calculation can be done very easily using this Parseval's theorem by evaluating the value of the integral a to b f x whole square dx. Now, let us see one example. We want to, from the Fourier series expansion of f x equals x square, we want to prove that summation n equals 1 to infinity 1 by n to the power 4, the value will be equals to pi to the power 4 divided by 90. If you see, remember, the Fourier series expansion of f x equals x square in minus pi to pi, x lies between minus pi to pi, is x square equals pi square by 3 plus summation n equals 1 to infinity minus 1 whole to the power n into 4 divided by n square into cos n x. Please note that this already we derived earlier. In earlier examples, we have obtained the Fourier series for the function x square in minus pi to pi, and directly I am writing this. Here basically your a naught, you can check it of your own also afterwards. A naught is 2 pi square by 3, a n equals minus 1 whole to the power n into 4 divided by n square, and your b n value will be equals to 0. So, you are obtaining the series of f x equals x square as this, where a naught, a n, b n are this. This you will calculate and you will check it whether it is coming properly or not, since we have done it earlier. So, I am not repeating this particular process. Now, from the Parseval's theorem, we know that this is equals to, you know, 1 by twice pi into minus pi to pi f x square dx. This is equals a 0 square by 4 plus half into summation n equals 1 to infinity a n square plus b n square. So, once I am getting this, from this is equivalent to, I can tell, 1 by pi minus pi to pi x to the power 4 dx. This you will obtain as pi to the power 4 by 9 plus half into summation n equals 1 to infinity 16 divided by n to the power 4. So, by putting the values of a naught, a n and b n. So, that if I evaluate again this, I will obtain 1 by pi into x to the power 5 divided by 5, say minus pi to pi minus pi to the power 4 by 9. This will be equals to 8 into summation n equals 1 to infinity 1 by n square. So, I am obtaining this thing. So, I can put this thing 8 summation n equals 1 to infinity 1 by n square. This is 1 by n to the power, this is n to the power 4, this should come as pi by 4 into n to the power 4, this is n to the power 4. So, this is also n to the power 4, this is equals 1 by pi into pi to the power 5 plus by 5 plus pi to the power 5 by 5 minus pi to the power 4 by 9. and from here summation n equals 1 to infinity 1 by n to the power 4. If I calculate, I will obtain the final value as pi to the power 4 by 90. So, therefore, the summation n equals 1 to infinity 1 by n to the power 4, this is equals pi to the power 4 divided by 90. So, effectively I had the series, I know the values of a naught, a n and b n from the earlier thing. Then I am using the Parseval's theorem, and from the Parseval's theorem I am showing that the value of n equals 1 to infinity 1 by n to the power 4 equals pi by 4 into pi by 4 divided by 90. Let us take another example. For the function f x equals x, which is defined in 0 to pi, and we know that half range sine series, half range cosine series is known to us. For the function f x equals x, we know the half range cosine series in the interval 0 to pi, and what I have to do? I have to prove that summation n equals 1 to infinity 1 by twice n minus 1 whole to the power 4. This is equals pi to the power 4 by 96. So, from the half range cosine series of the function f x equals x in 0 to pi, I have to prove this thing, summation n equals 1 to infinity 1 by twice n minus 1 to the power 4 by pi to the power 4 by 96. Now, half range cosine series of f x equals x is x equals pi by 2 minus 4 by pi into summation n equals 1 to infinity cos of 2 n minus 1 into x by 2 n minus 1 whole square. Again, half range cosine series already we have done earlier. So, I am not repeating the process. So, your half range cosine series of f x equals x is this, where your a naught equals pi and a n equals minus 4 by n square pi when your n is odd. Please note that in earlier lectures we have evaluated this thing when and the value of a n is 0 whenever n is even, and your b n value is equals to 0. So, once I am getting this from Parseval's theorem, directly I can use this one. I can use the coefficient values of a naught, a n and b n, and I can substitute in the Parseval's theorem, so that I will obtain in the same fashion whatever we did earlier. You will obtain the value of this by substituting in the Parseval's theorem. I will obtain 1 by twice n minus 1 whole to the power 4. This ultimately you will obtain pi square by 8 into pi square by 12. So, that the value is pi to the power 4 by 96. So, therefore, using the half range cosine series of f x equals x, which is defined in the interval 0 to pi, we are getting that the value of summation n equals 1 to infinity 1 by twice n minus 1 whole to the power 4 equals pi 4 by 96. I skipped the certain steps over here, because the problem is similar as we have done in the earlier examples. Substitute the values of the coefficients a naught, a n and b n in the Parseval's theorem, and by substituting that and by simple manipulation always you can derive this value, that summation n equals 1 to infinity 1 by twice n minus 1 whole to the power 4 is equals to pi to the power 4 divided by 96. So, effectively this Parseval's theorem is very useful in electrical engineering cases, electronics engineering, where they have to calculate the RMS value, and for calculating the RMS value, the effective value of the function, efficient value of the function, we try to use this Parseval's theorem and try to find out the value of a to b mod of f x whole square, f of x whole square dx, and using that one we find the some other cases. So, I hope you have understood the Parseval's theorem and its application. Thank you.